Hey folks, Mash here, and today we'll be doing the paper 2, 2019 higher chemistry paper. That was lovely, wasn't it? So, yeah, we'll get straight into it. So, sulfur thiosulfate can be used to investigate the effect of reaction conditions on the rate of reaction. Sodium thiosulfate solution reacts with hydrochloric acid to form a precipitate of solid sulfur. By placing the reaction mixture in a conical flask over a cross and recording the time taken for the cross to disappear, the effect of changing the reaction conditions can be investigated. Okay, we got here, and you can say, oh yeah, we add hydrochloric acid, and then it slowly turns opaque, and we can see the cross disappears. So the equation for the reaction is this: balance the equation. All right. So when we say balance equation, we just need to make sure that both sides have the same number of atoms of different elements. So what I'm going to go through here is I'm saying, okay, well, first we can see we've got 2 sodiums here, and we only have 1 on this side. So as a quick fix, let's just go and double it. And then I'm going to go again. I'm like, okay, well, we have 1 chlorine atom on this side, and we have 2 on this side. So let's double that. And again, we're just going to go and check to make sure that I'm, not going completely insane. And see if there's everything else is okay on that side. But so far it looks good. We have 2 hydrogen atoms. We have 2 oxygen atoms there, 1 oxygen atom, so that means 3, 2 sulfur, and yeah, it seems to good. So that's all you need to do. And yeah, that's it. It's only a mark, so it's not that difficult. In one set of experiments, the effect of varying the concentration of sodium thiosulfate was investigated. Complete the table to show the volumes of water that reuse the varied concentration of sodium thiosulfate. So this one is almost insultingly easy. What we need to do is figure out the numbers that add up to 50. Because you can see here, that's 50, and 10 plus 40 is also 50. Which means water in this column would be 10, and then 20, because 20 plus 30 is 50, and then 20 plus 30 will be 50. So yeah, that's what you need to do. Calculate the time in seconds for the cross to disappear in experiment C. So where we do this is remember that to calculate relative rate, it is 1 over time. So if we want to calculate the overall time, what we would do is it would be 1 over r of the rate to equal time. We just need to do the same thing. So it says it's cross to experiment C. Experiment C is this one. We have 0.0285, and then all I'm going to do is invert it, and we're going to get 35.08. And I'm going to round it to 1 decimal place, so it'll be 35.1 seconds. Splendid. We'll go on to the 3. The reaction can also be used to investigate the effect of changing temperature on the rate of reaction. The results from the investigation is shown in the graph below. You can see here. Use the graph to determine the temperature rise in degrees Celsius required to double the rate of reaction. So what we want to do here is we want to find a doubling, right? So let's go and pick points that are very clearly marked. So 2 and 4 could work, but 4 is kind of in the middle there, so it'll be a bit iffy. But the ones I chose for, I would probably choose this one. They are, thinking 4 is going to be a bit iffy. How about we go for, let's go 5 and 10, right? Because this one here, this point here, that's exactly in the middle of relative rate. So this would be 0.05 here, and then if we go up to 10, we find that we've got exact point there for 0.01, I suppose. So now all we need to do is find the distance between these 2 points. So 0.05 here, that is at 60, and with 0.010, that is at 72, which means difference between 60 and 72, that's 12 degrees Celsius. Move on to B. Collision theory states that for particles to react, they must first collide with each other. State 2 conditions necessary for the collisions to result in the formation of products. So 2 things here. Particles must have at least as much kinetic energy as the reaction's activation energy. I can spell activation. Energy. And because there weren't two conditions, they need to be orientated. If I can, as you can see, I'm not amazing at spelling. Orientated correctly. And there we go. That's all you need to do. We got two conditions for 2 marks. Sodium thiosulfate also reacts with iron-free nitrate. The potential energy diagram shows the change in potential energy during the reaction carried out without a catalyst. Draw an X on the potential energy diagram to show where the activated complex is formed. So remember, you just kind of remember this: when the activated complex is formed, it would be at the highest, the peak. It would be at the peak of this thing. So that's where that's the kind of midpoint between two stable reactive states. This is everything's mixed together, and then these would be the products, and these would be the reactors down here. I'll stop blabbering on, but copper 2 ions catalyze the reaction. Add the dotted line to the diagram to show the change in potential energy with the catalyst. So remember, the reaction will be the same. So it would still be from these 2 points, but the dotted line would be a different reaction pathway at a lower activation energy. So if there's low activation energy, the peak would be lower. Let's make it way lower to make it obvious. Say there, and then. But it will still follow the general same shape. It would just take a bit less energy. And there we go. Move on to 2. 2019 is the 150th anniversary of the periodic table by Dmitry Mendeleev. The patterns identified by Mendeleev form the basis of the modern periodic table. The major periodic trends include ionization energy and covalent radius. The first ionization energies of elements with atomic number 1 to 20 are shown in the graph. Explain why the first ionization energy shows an increase from going from lithium to neon. Okay, so what happens here is this is only 1 mark, so you don't actually need to say too much for this, but I'm going to say a bit more just because then you can slot it in for more advanced questions. So you can say going across a period, increases the number of protons within a nucleus, and technically, yeah, this will actually be enough to get you the mark in this case. But just to really cover all bases, I'm going to say this increases nuclear charge, which increases the force of the nucleus on the electrons, increasing ionization energy. So yeah, that's more than enough. That's way more than enough actually for this this mark. I say outer electrons. But it's probably always better to write more than write less, you know. So yeah, this should be completely fine. Right. We'll move on to 2. I'll explain why the first ionization of potassium is less than the first ionization of lithium. So as we can see on this graph here, first ionization energy of potassium is a lot less than lithium. And the reason is because if we look at our data booklet, we're going to have a look at potassium lithium. You can see lithium's got 2-1, but potassium has more electron shells. So what does this mean? That means that this electron here, this outer electron, is less shielded from the force exerted by the nucleus than potassium, because there's less inner shells. So that's what we're going to write. Potassium has 2 more inner shells than lithium. So the outermost electron extend this out is better shielded from the force exerted by the nucleus than when compared to lithium. I'll just clarify here, outermost electron of potassium. So ionization energy is lower. There we go. So you want to use shielding, the word shielding or screening in this. I always use shielding. I just think I don't like screening for some reason. It's just one of those irrational things, but either one is fine. But the main point in this is the shielding. Move on. A graph showing the ionization energies for nitrogen is shown. And as you can see here, there's a very steep increase from 5 to 6. And it wants us to write the equation for second ionization energy of nitrogen. So if you want to be lazy, which you mean, yeah, you want to be as lazy as possible in an exam, that's not a joke. What I recommend is going for your data sheet, because this will actually tell you exactly what you need to do. So it says second ionization of nitrogen. And look at that. Second ionization of energy refers to this equation here. So let's actually go and, if I can multitask here, let's just copy this down. So all we need to do is replace E with N in this case. So we have N, I'll make it slightly simpler, N plus G. Remember, we always have the G because we're assuming these are gaseous ions. 2 plus, remember the G again. And then plus a single electron. And there we go. That's all you need to do. We're then going to have explain fully the increase between the 5th and 6th ionization energies of nitrogen. So, well, let's go back to our data book. I might just keep this open at this point. Scroll along here. We can find the electron arrangement of nitrogen, and it's 2 and 5, which means the reason that we have this massive increase is that once you knock out 5 electrons, you're going to be taking it from its innermost shell, which is closer to the nucleus and less shielded by inner shells, because there's no inner shells, which means that the ionization energy will be massively higher. And so, yeah, that's exactly what we're going to write. So we're going to say the 6th ionization energy removes an electron from nitrogen from an inner shell which is closer to the nucleus and less shielded by inner shells So the force exerted by the nucleus, I know how to spell nucleus, I swear, is stronger, and so ionization energy increases. Ionic radius is the measure of the size of an ion. Explain fully why the ionic radius of phosphorus is greater than the ionic radius of aluminum. So let's have a look at this. We can see that aluminum's got the electron arrangement 2a3 and with phosphorus got 2a5. So that means ionic radius, remember, it's the size of an ion. So aluminium's ion would be 2,8 and phosphorus would be 2,8,8, which means that phosphorus got an entire extra electron shell, so it'll increase its size, you know. More layers to an onion, the onion will be bigger. So we can say aluminium ion would have the electron arrangement of 2,8, while phosphorus's ion would have the electron arrangement 288. This means that the phosphorus ion has an extra electron cell compared to the aluminium ion, so it is it has a larger ionic radius. There we go, that should do it. The structure of an ionic compound consists of a giant lattice of oppositely charged ions. The arrangement of ions is determined by the radius ratio of the ions involved. Radius ratio is the radius of positive ion divided by the radius of the negative ion. And we've got two examples here. We have cesium chloride, which has got 0.96, and sodium chloride, which has a radius ratio of 0.52. By using the table of ionic radii on page 17 of the data booklet, it's not actually the key, they keep changing it, predicts whether the structure of barium oxide is similar to cesium chloride or sodium chloride. So, I'm going to scroll down. It's not page 17, I think it's 18. Yep, there we are. Ionic radii selects ions. So, we want barium oxide. So barium is somewhere around here. Am I just blind today? Probably. Oh, there we are. It's a positive ion. So according to our thing, we need to put it on top of our thing. So we've got 135 picometers, and then oxygen is -2, so it'd be negative, obviously. So it'd be 135 over 40. Now, if we pull up our fancy dancy calculator, we're going to 135 divided by 140, and that will give us 0.96. So therefore, the structure of the barium oxide would be more similar to cesium chloride, and there we go. The melting point of non-metal elements depends on structure and bonding. Using your knowledge of chemistry, comment on this statement. Okay, so I guess we should lay this out into groups. There's going to be one big text box. But let's think about some ways that non-metal elements bond. So we've got monoatomic, and that's basically for like noble gases. Right, so yeah, we're going to make a list of all the different things. So we've got monoatomic, so these are noble gases. And then for other ones, we've also got discrete covalent. So that's that was stuff like diatomic elements, mostly diatomic with a few exceptions. And then we've also got ionic, or non-metal elements, sugar. Before I forget, we've also got giant network covalent, which is stuff like diamonds. So yeah, these are probably yeah. So whenever you do these 3-mark questions, it's probably best to make a nice wee list of them. This is what you're going to talk about. And so I've made 3 things here. So if I do it in quite good detail, I'll easily get those 3 marks. Yeah. So I'll just start blabbering on. So monoatomic elements are elements that exist as a single atom for the only intermolecular forces between them are LDF, London dispersion forces. We can talk about them if you want. We can go into detail about it. So dispersion forces, which are relatively weak, due to the small number of electrons per atom. This means that monatomic elements are almost, I mean, I think we can say always, because if we look at the periodic table real quick, all the monatomic elements are on the side here, and yeah, they're all gases, so always gases at room temperature and pressure. They also do not have, they also cannot make chemical bonds with other atoms under normal conditions, because you can actually get weird compounds with like xenon and whatnot if you put them in a very high pressure, but this is not covered in higher chemistry, and we don't need to go into much details about it, so you can just say under normal, they don't do anything under normal conditions. Yeah, but I think we've covered mostly structure and bonding, so let's go move on to discrete covalent. Molecules are elements that exist as covalently bonded molecules, individual molecules I should say, and that's another thing we can talk about covalent bonds, but I'll get the standard stuff down first. I'm really sorry for my spelling, it's horrific. Elements exist as covalently bonded individual molecules with with LDF forces between them. All the elements, all the molecules are all of them, the covalent bonds are non-polar because there is no difference in electronegativity. Because if you just have, an element, there's going to be no weird atoms, unfortunately. So you're always going to have non-polar bonds. There's no PD interactions for hydrogen bonding. Oops, excuse me. It includes diatomic elements, which you can give some examples here. So I always remember as H-NOF down, which is like hydrogen, if I could spell it right, hydrogen, nitrogen, we'll go oxygen, etc. Are molecules made of two atoms covalently bonded together, usually gas at room temperature and pressure, but the heavier ones like bromine and iodine are liquid and solid, respectively, because bromine is liquid at room temperature and iodine, I believe, is solid. Solid at room temperature and pressure. Because they have more electrons, meaning the LDF forces are stronger. Thus harder to break. And then we can talk about the exceptions. So we've basically it's sulfur and phosphorus. Sulfur forms S8 things, and then phosphorus forms P4, and they're both solid at room temperature because of the extra electrons in each molecule, because you know there's 4 of them. Sulfur forms a molecule with 8 sulfur atoms. Covalently bonded together. And the molecules are attracted to each other via LDF. The increased number of electrons in each molecule means that sulfur is solid at room temperature. Right, and I'll just go and add in here about phosphorus. It might not be entirely grammatically correct, but you know what? You're not watching an English channel, you're watching a chemistry channel. So here we are. Solid and phosphorus are solid at room temperature. So then we just got to talk about nitrogen covalence. Sorry. So giant network covalents are large structures where all atoms are bonded covalently to each other. And thus have high melting points. Yeah, I have just realised I got to tie everything back to melting points. You might just see me add in. It's really easy when you do these questions to just get kind of carried away and not actually answer them, which, yeah, it happens to the best of us, as you can see. So I'll just go and make sure clear. But I am talking about it's being solid room temperature, so I just need to make it slightly more clear to make sure I get those marks. Melting points as covalent bonds are very strong and require a lot of energy to break. Examples are boron and carbon in diamonds. And just I'll go and add some more examples in here, because you also get carbon. I'll add carbon fullerenes in here. Carbon can also form fullerenes of 60 carbon atoms covalently bonded together. So yeah, I think this is, we've already rolling quite a bit, so I'll just go and make sure that I've really tied it back to melting point, and then we should get ton of marks. Always gases at room temperature, so have incredibly low melting points, as little energy is required to overcome the LDF between the molecules. And I'll just get rid of this pressure bit. Oh, I need to actually spell molecule correctly. So this is taking ages. This is whenever you do these questions, make sure you leave them to the end, because as you can see, they just take absolutely ages to do, and they're only 3 marks really, so they're pretty inefficient in terms of that. So I recommend you just do it later. It's just not worth it. Oh, should we just leave it there? Room temperature, as they have. Yeah, well, I think we'll just leave it there. It's sort of there. Just make sure you tie it back there. I probably should have done that. I could have done that a bit better. But anyway, we'll move on to stuff I can actually do. So what we have here is cider is made from apples in a process that involves crushing and pressing the apples, converting the sugar into alcohol, maturing and bottling. Brewers yeast, which contains a mixture of enzymes, convert the sugars in the apples to alcohol and carbon dioxide. The state is what meant by the term enzyme. This is pretty simple. It's just a biological catalyst. That's just one of the things you gotta remember, unfortunately. But yeah, that's it. Biological catalysts, because they speed up a reaction without getting changed in the process, but also they're made by nature to be biological. The percentage mass of alcohol in the cider can be calculated using the formula percentage mass of alcohol equals mass of alcohol over mass of cider times 100. 50 cubic centimeter sample of cider was found to contain 3.05 grams of alcohol. 1 cubic centimeter of cider weighs 1.36 grams. Calculate the percentage mass of alcohol in cider. So yeah, we all need to do here is basically plug numbers in here and see what happens. So I'm just I'll pull up my fancy dancy calculator. So mass of alcohol, it says that it's 0.045 divided by mass of cider, and it says 1 cubic centimeter of cider weighed 1.36, and we've got 50 of it, so we're gonna go and times that by 50. Oops, if I knew what I was doing. I'm gonna reset that. Oh, it's been a long day. Not really, I'm just really bad. But yeah, so 1.36, and then we're going to times it by 50. Beautiful. And then divide it, and then of course this doesn't look much sense, but we just times it by 100 to get the actual percentage, and it's 4.5. So we'll just write that in. There we are. Okay, so during the maturing process, maltic acid is converted into lactic acid and another product. Oh, excuse me. It's very hot out here, I'm afraid. So, but what we want to do here is see what's missing from this compound. So, maltic acid converted to lactic acid and another product. So, we're going to have a compare these two, see what's the difference. And what I'm seeing right now is, well, we're missing a carbon. Missing oxygen, missing another oxygen, but that hydrogen there is accounted for here. So that means X is going to be carbon dioxide, because there's 2 oxygens and a carbon. And yeah, a lot of these times you'll find carbon dioxide crops up quite a bit, especially when you're dealing with alcohols. So it's one of those chemicals you names you can just throw in there. If you don't know something, put carbon dioxide or put water. It's probably one of those two, to be honest. The maturing process in which cider samples can be monitored using thin layer chromatography. Samples of lactic acid, maltic acid, and ciders A, B, C, and D are spotted on a silica plate, and the solvent is allowed to travel up the plate. The chromogram attained is shown below. You can see here it's got things go up. So basically, heavier things. I mean, yeah, stay in the sample for longer, I believe, and then. No, excuse me. But yeah, we don't need to worry about that too much. We can just go and start running in. So as you can see here, yeah, heavier things slow down, so they don't move so much, but lighter things tend to go further. As you can see here, because maltic acid is bigger, it's got carbon dioxide compared to lactic acid. But it also depends on structure and body. It's a whole subject. Okay, I won't get into it, but too much. But for this question, we won't need to know too much about it. So the retention factor R for a substance can be a useful method of identifying the substance. And R is the distance moved by the substance divided by distance moved by the solvent. So it wants to calculate R value of maltic acid. So maltic acid moves 4.1, and then we want it to divide. It wants us to divide by the solvent, and the solvent has moved 16.4, which means the R value is 0.25. The maturing process is complete when all of the maltic acid is converted into lactic acid. The cider is now ready to be bottled. Use the chromogram to determine which cider is ready to be bottled. Okay, so all the lactic acid should we only see lactic acid in here. Well, if you have a look around, so some of them have two spots. That means there's both maltic acid and lactic acid in there. An 8.2 corresponds to lactic acid as shown here. Maltic acid plus 4. So we just want to find the cider that just has 8.2 in it, which is cider B, because cider C hasn't even begun getting converted, and cider A and D is still in the process. So that's what I'm going to put down. So cider B. Glycerol can be added to cider for bottling to produce sweeter tasting cider. Say it's systematic name for glycerol. Again, this is going to be again one of those just things you just gonna have to know. It's going to be it's propan 1, 2, 2, 3 trial. This comes up a lot in fats and oils and whatnot. Cider contains many naturally occurring compounds that affect taste and aroma. Procyanin B2 provides a bitter taste to cider, which is because this massive molecule here. Explain fully why procyanin B2 is water soluble. Well, you can see here is there's two things that are good if you want to be water soluble. Is is you want to have polar bonds or you want to have hydroxyl bonds and you, be able to form hydrogen bonds. And well, you've got it in spades here. This is because of all these hydroxyl groups. You can form hydrogen bonds, and it's also polar, so that's cool. And then all you need to do then is say, okay, well, since it can form hydrogen bonds, or since it's a polar molecule, it's a lot more soluble in water. So that's exactly what we're going to do. So pro cyanogen B2 has lots of hydroxyl groups that make the molecule polar and able to form hydrogen bonds. Water is a polar substance and can also form hydrogen bonds with molecules, so will dissolve procyanin or whatever B2 easily. Yeah, and I think that's all you need to go and write in there. Cider smells of apples because it contains ethyl 2-methyl butanoate. So sorry, just double checking my answer to the last question. I do get kind of paranoid myself. But anyway, so cider smells of apples because it contains ethyl 2-methyl butanoate. The carboxylic acid used to make ethyl 2-methyl butanoate is what? Well, when you ever have an ester like this, the carboxylic acid would be the one name on the end, or the name with the on the actual molecule. It would be this one over here. It would be the carbon with the O, the double bonded O connected to the O on this side. So that's exactly what we're going to write in. We're going to say it'd be 2-methyl butanoic acid. There we go. Yeah, all you really do is replace the OH with oic acid. Farnesene is a terpene responsible for the ripe apple aroma of cider. Name the molecule in which terpenes are based. So two things here. You can just say isoprene, as we said before in a multi-choice, or you can say its full systematic name, which is 2-methyl. Bear with me here. This is going to be a nonsense. Butan 1,3 diene. I might have said butan rather than butan in the previous video, but here we are. We can say either of these things. Probably go with isoprene because it's easier to remember rather than 2-methylbutan 1,3-diene. Like, rubbish. Ethanol and cider can be oxidized to ethanal, spoiling the aroma. Name the functional group circled in the ethanol molecule. Clearly see here, this is going to be a carbonyl group. So carbonyl groups, they're just double bonded oxygens to the carbon. And I guess you could have also, yeah, it'd just be carbonyl. Yeah, you just say carbonyl. It's a better bet than ketone or aldehyde. That's not really what you're supposed to be doing. You should be saying carbonyl. Further oxidation of ethanol can produce another product that spoils the flavor of cider. So name this product. So, well, it's ethanol, so that means you can actually oxidize this even further into a hydrochloric acid. Hydrochloric acid is sour, so it would ruin the taste of cider because it's nice and sweet. So that's what we're just going to write. We're just going to write ethanoic acid. If it was FN1, which it doesn't exist, but if it was a propane 1 or something, you couldn't oxidize any further because it's a ketone. The combustion reactions of methane and heptane can be studied in different ways. The combustion of methane produces carbon dioxide and water vapor when carried out at temperatures above 100 degrees Celsius. Using bond enthalpies and mean bond enthalpies from the data book, let's calculate the enthalpy change in kilojoules per molar for this reaction. So what we're going to do here is I'm going to go and I'm going to get some lines and make a table. So what we're going to have here is bonds broken, and bonds broken require energy. So even though require energy, there'll be a plus because yeah, remember in chemistry, negative enthalpy is giving out energy, plus is requiring energy. It'll be endothermic. Then bonds made would make energy, so there'll be negative. Cool. So next, what we're going to do is going to scroll down to our selected mean bond and mean enthalpy bonds on page 11, and we're going to start running through. So on here, I can clearly see with a methane molecule, that means that 4 times C2H is broken, which means that we're going to add 4 times the CH is going to be on our mean table. It'll be 412. So 112, i.e. we'll just compute that straight away. Now we'll leave it. Yeah, we'll leave this for later. So 4 times 12 kilojoules per liter per mole, and then we'll move on to the oxygens. So each oxygen atom only has 1 oxygen double bond, but there's 2 oxygen atoms, so we're just going to have 2. There's oxygen double bond, which is over here 498. That's 2 times double bond. I put an equal sign. There we go. And then that's all that on that side. So now let's see what bonds we've made. So we've made 2 carbon to oxygen double bonds. So I'll put that in. And a carbon to oxygen double bond is 804. And then we've made O to H. We've made 4 of those bonds because each one molecule contains 2. Well, if we've got 2 of them, that's what we're going to write. And that would be, go over here to C and H, probably I mean, not be O and H, wouldn't it? Go over here, O and H, it would be 463. Right. Now all you need to do is add these all together. So I'll start with 4 times 4, 112 plus 2 times 498. So that'll give us a total of 2,644. And then we're going to take away these 2. So let's just go and put some brackets around. 2 times 804 plus 2 times 463. Do that. We get oh, did I just put 2 for both of them? Okay. Apologies for that. I was wondering I was getting a silly answer. So yeah, remember to double check, especially for this one. If it's because this is obviously a combustion question, so you should always be getting a negative answer unless it's something really weird. And this is not weird. This is combustion of methane. Like, this is used all the time. But yeah, sometimes I make mistakes. So there we go. Minus 816. Alright folks, I'm back. So yeah, I was really wondering why I flipped everything up here, but it turns out I hadn't. I actually got the correct answer, minus 816, but it's not in the answer scheme because I'll go and bring this round if I can. Notice anything weird about this, right? Where did 743 come from, you may ask? Yes, that's right. This is a slightly old past paper, 2019. So that means that they've changed the bloody data booklet. So yeah, so when you're doing these, be careful for that, because you just have to check the marking scheme and make sure you know what you're going about. But we all know that that was totally correct. So we're just going to say 8x mules and then to the power of minus 1 when you add them all up. So yeah, sorry about that, folks, but it's not really my fault, is it? Right. Explain the difference between bond enthalpy and mean bond enthalpy. Basically, bond enthalpies are measured in diatomic molecules, or like what your single. The whole molecule is just that bond, nothing else. So it's quite easy to measure because you can just be like, oh, I'm going to put so much energy in and see if they break. But mean bond enthalpies, because of the all the other atoms in the molecule, they're going to pull electrons in weird ways, which means you're taking an average of what the bond is, because in some situations it could be worth more, in some situations it could be worth less. So that's what we got to say. So I mean bond enthalpy calculation based on many molecules, based on the average energy over multiple molecules, while bond enthalpy involves one molecule So yeah, it's because there's lots of molecules that use CH, but there's only really one molecule that uses HF, for instance. Right, and we'll move on. Calculate the mass of grams of carbon dioxide that would be produced by combustion of 200 cubic centimeters of methane and excess oxygen. To take the value of 1 mole of methane gas would be 24 litres. So, what we're going to do here? Well, we're going to go and use the often underrated molar formula, which is N equals V over the molar V. So we know it's 200 cubic centimeters, and we always do this in liters, so it's going to be 0.2 over 24. Run that through our calculator. That'd be 0.083. Fantastic. So now that we know the amount of moles of methane we have, we can extrapolate to carbon dioxide. We can use N equals FM. Now it actually tells us the formula mass is 44. And we know the moles thanks to our molar volume. Oh man, I hate this so much. There we go. So now we just need to times this by 44 and we should get our answer, which is 0.36, so 3.37, you know. And remember your units, it's grams. The enthalpy of combustion of heptane, C7H16, can be determined using a colorimeter. The following results were obtained. Stating the measurements required to calculate the mass of heptane burned in this experiment. So, well, think about it. What would you do? Well, I would probably take the heptane burner, measure it beforehand, and then you measure it afterwards and calculate the difference. So let's go and do that. You can say initial mass of the heptane burner, then mass of the burner after the experiment, and that's it, because it doesn't actually tell you to do any calculations, but just for the fun of it, I'm just going to say then find the difference. Calculate the enthalpy of combustion in kilojoules per moles for heptane from the experimental results given. Okay, so just wants us to know empathy. So there's going to be a few things we need to do here, but so the volume we want to use. Okay, so first thing to do this is remember that empathy, it's got the formula delta H, which is empathy is energy E over a number of moles. So we're going to work out E first, and then we'll work out N, and then we can work out the empathy. So luckily we've got it's heating water, so I can just go and use the general heat formula, which is MC delta T. So mass of water, it's going to be, we always work in kilograms. So since it's 400 cubic centimeters, that's going to be 0.4. And then we're going to be times it by 4.18. And then what is the change in temperature? Goes from 26 to 49, which would be 23. And then we'll go and multiply all this together. That'll be 38. Oh god, mate, this software sucks. 0.46 kilojoules. Okay, cool. And then we just work out the number of moles. So this will be number of moles of heptane burned. So it says mass of heptane burned is 1.1. And it says the mass of 1 mole of heptane is exactly 100 mole. 100. So we just can do that and then do our calculation. So it'd be 0.011 mole. And now we can scroll over a bit and we can go and put our delta H equals E over N. E is 38.46. I'll put 456 just to be extra accurate. And then 0.011, and then we can finally do it. So oh, cheers, that's really helpful, isn't it? Fine, we'll do it out the old-fashioned way. And that will lead us with 3,496 kilojoules per mole. There we go. The theoretical value for the enthalpy of combustion of heptane is significantly higher than the experimental value. Suggests why the experimental value is different to that of the theoretical value. And this is basically, you can just use a standard thing here, because heat was lost to the environment. Because when you calculate the theoretical enthalpy, you wouldn't consider stuff like the heat getting lost in the environment. You would just pretend that didn't exist in a perfect, beautiful world, you know, that we all love to live in. So, we'll move on to 6. Thiols are compounds that contain a SH functional group. They often have very strong, unpleasant odors. Ethanol is used to add a smell to gaseous fuels in order to give warnings of gas leaks. And we have it right there. A student used the boiling points of ethanol and propan-1-O to compare the strength of intermolecular forces. State a reason why propan-1-O is a suitable alcohol to compare with ethanol. Whatever it is. Ethene thiol. There we go. So yeah. Well, whenever it says this, it usually means that they want the same amount of electrons in both molecules, so that LDF is the same. So that means they can compare the strength of PD-PD. So let's go and have a count up all the electrons. So carbon atom has 6 electrons, so with 2 carbon atoms, 12. Then 6 hydrogen atoms, so that's another 6 added on, so we're at 18. And then how many does sulfur have? We've got 16. So 16 plus 18, well, that's 34. And now we'll see about propan-1-O. So 3 carbon atoms, that's 18. We have 8 hydrogen atoms, so that's going to be 26. Yeah, 26. And then oxygen has 8. So 26 plus 8 is 34. And that's what we're going to write. So yeah, we'll just double check they both have the same amount of electrons. So you can say both molecules same number of electrons. So strength of LDF is the same. Explain why propan-1-O has a higher boiling point than ethene thiol. The answer should include the names of the intermolecular forces broken when each liquid boils. So, well, if you have a look at here, right, this one, they both have the same number of electrons. So LDF is the same as previously established, but this one is bonded to this hydrogen bonded to O, which means propan-1-O can make hydrogen bonds with itself, which are very strong, stronger than normal PD-PD interactions. Okay, so propan-1-O has a hydroxyl group, so can form hydrogen bonds with other molecules, so which are much stronger than PD. We could say actually it's got the full name, permanent dipole. There's dipole, permanent dipole interactions. So require more permanent interactions, which are the strongest. Van der Waal, which are just fancy name for intermolecular force in EFAN file. So propan, the forces holding propan one altogether require more energy to break than EFAN, whatever file, thus have a higher boiling point. Oh, that was an awful. Probably don't need to say too much for that 2-mark question, but I'm always of the write more than you think you need. And there we are. Name the file that contains only one carbon atom. Oh, this is a nice easy one. So if it's ethan file, that means that one that only has one would be methan file. There we go. The minimum concentration of ethan file in air that can be detected by humans is 2.7 times 10 to the negative 7 milligrams per cubic centimeter of air. Calculate the minimum mass of ethanol that needs to be present in a room containing 43,900 litres of air in order to be detected. Okay, so 43,900 litres. We want to convert that to cubic centimetres, which means we times it by 1,000. So that would be, I'm going to write it out. Be 43,900, 1, 2, 3, and then I'll put some commas in to break things up. Cubic centimeters, and then we want, this is per milligram, milligram per cubic centimeter of air, so we want to times this by 2.7, which is itself times 10 to the negative 7, and then this is in milligrams, so we'll have to convert it to grams or something sensible. But let's go and actually just straight do the calculation. So 43,900, there we go, this big number, times 2.7, and then boom, so this is how many milligrams. 853 milligrams. And yeah, I guess you could just leave it there if you wanted to be, just keep it as is. But you can put it also into grams or kilograms, but looking at this, it's probably just a bit inappropriate. And they will actually let you keep all 3 decimal places, and I like my accuracy, so I think we'll keep it as is. Okay, so let's move on. 2-methyl-2-propanethyl is also used to add a smell to gaseous fuels. Suggests why 2-methyl-2-propanethyl is classed as a tertiary fuel. Well, that's because the tertiary group, as you can see here, is bonded to a carbon atom, which is bonded to 3 other carbon atoms, like tertiary alcohols. There you go, that's it. Thiols can be easily made, well, can be made by the addition of hydrogen sulfide to alkenes. 2-methyl-2-propene-thiol can be made by the addition reaction shown. Okay. Draw the structure for the other isomer formed in this addition reaction. So isomer, remember, isomer just means a molecule that has the same molecular forming but different structure forming. So it's like if you took a molecule and kind of rearranged it but keeping all the same pieces. So in a lot of reactions, you'll actually get more than one product, but there will be isomers of each other. So you can just kind of, it's like rearrange a bit, so it's slightly different. But as you can see here, what would happen is you'd have the SH group on another carbon. So instead of having it in this middle carbon, you have it on this one over here. So let's go and draw this out. Remember, it should be a double bond. Whoops. This would be H rather than SH, and this would be SH up here. And then everything else would be hydrogen. A chemist obtained an 84% yield of 2-methyl-2-propene and thiol after starting with 30.5 grams of 2-methylpropene. Calculate the mass of grams of 2-methyl-2-propene made by the chemist. Okay, so this is a yield question. So I'll go and make this full screen. Actually, that might handle out. So remember, percentage yield. I just use percentage y equals theoretical mass. No, what am I? Real actual mass, I guess. Over theoretical mass. Times 100. So what I want to do here is figure out the theoretical mass of what we could get if we had 30.5 grams of 2-methylpropene, and then it tells us what we actually got, and then we can plug it in here and we'll get what they actually got, the chemist. So 30.5 of 2-methylpropene, if we go up here, if we can use, it gives us our general formula, so we can actually just straight up start doing some calculations. So let's calculate the moles of 2-methylpropene that the chemist used. The formula mass is 56. So that gave us 0.045 moles. Cool. So that's how many moles of this we have, and then notice this equation, the molar ratio is 1:1, so it's going to be the same number of moles. And then we're just going to calculate how much mass they got out of this one. And the formula mass is 90.1. So essentially we just need to times this one by 90.1. And I times it by 900, and I'm going to blame Windows Calculator on that and not my own ineptitude. But we'll try that again. that'll be 49 grams essentially. I'll give them 49.07. So now that we have that mass, but they only obtained, so that's what they attained in the thing. That's what you would attain, sorry, if you had the best setup ever and you got 100% yields, but obviously it never happens. So instead, what we're going to do is we're going to plug the numbers back into this equation. So we have 84 equals, this is actual mass, so they this is what we want to figure out. I'll just put it as AM. And then we know that the theoretical mass is 4.9, well 49.07 times by 100. So I'll do some quick algebra because there's already a lot I can't. So basically what I'm going to do is divide this. We're going to turn this into a decimal form. So we 0.84 to get rid of this 100, and then we're going to times it by our theoretical sample. So 0.84, and that gives us 41.2 grams. And there we are. Oh, that was a long one. Esters can be synthetic or natural. The synthetic polyester PET, polyethylene tetrafilate, has many ester links. PET can break down a free radical reaction. One of the steps involved in breaking that can break down by a free radical reaction. Sorry. One of the steps involved in breaking down PET is as shown. So state a name for the step. So you can see here, it's free radical that gets split apart into a free radical and a stable-ish molecule, and that would be a propagation step because it's not a stable molecule freeing; it's an unstable molecule breaking apart and then releasing more free radical radicals. So it doesn't end or start the cycle; so it'll be propagation. Boom, boom. Name the component of sunlight that can cause plastics of PET to break down. It will be ultraviolet. I think I just said ultraviolet. Ooh. Oops. Yeah, that's a bit better. Name the type of substance that can be added to plastics to prevent them from breaking down this way. So that would be free radical scavengers. Yeah, so I think there's a lot of chemistry, just a lot of stuff that you just kind of have to remember. But ultraviolet is like UV, so that's why you put it on sunscreen. It's just because you can cause free radical reactions in your own cells, and that's not good for your cells. You know, causes skin cancer and all that jazz. So with free radical scavengers, kind of stop that because they see free radicals and they stop them from causing any mayhem before they can do it. So natural cyclic acids called lactones can be formed from hydrocarboxylic acids. 5-hydroxypentantoic acid, oh my god, these names, is a hydroxycarboxylic acid. When heated with dilute acids will form a cyclic ester. Oh, what a hate chemistry, mate. This is horrific. So name product Y in this reaction. And this one is actually surprisingly simple despite all these stupid bloody names, because remember, when you join an ester to itself or another ester, it's something called a condensation reaction, where two molecules join, in this case the same molecule, but it releases water. Told you, if you ever says name product Y and you've no idea, water or carbon dioxide, pick one. It'll get you farther than you think. So draw the structure for the cyclic compound formed when 4-hydroxypentanoic acid is heated with dilute acid. Bleh. Right, let's go and figure this one out. So, yeah, let's just go and do it. So, let's draw this inner ring here first. So I'm going to have CH. And then it will be connected to what was originally the OH group, but it's now going to be our ester link, where we go to our carbon with the oxygen, and then we'll go down to this one over here, so that's CH2. And then we go to another CH2, and then we arrive back this one here, but we need to remember this. This one is kind of outside the circle, so I'm going to write it out here. And there we are. Beautiful, isn't it? Mwah. Could easily go on Louvre, right? In the Louvre, couldn't it? So name the hydroxylic acid shown below. Hydroxycarboxylic acid shown below. Oh, kill me now. So, let's just go and see what we get. So, going through here, well, I noticed there's 4 carbon atoms, so it's probably going to be butane. There's going to be a butane somewhere. I'm just going to write butanol because notice all these are just straight linear molecules, and so I think the number is when this hydro group is going to be put in. So this we always count along the way, so get the numbers as low as possible, because this count from this functional group here. So that means that 1, 2, 3. This will be at the third, so it'll be hydro, and then it's oxybutanoic acid. Yeah, so this one's a bit tricky, but I'm sure you can get through it. And we're moving on to 8. Gelatin is a soluble protein that can be added to different food products. A structure for a section of the protein chain of gelatin is shown. You've got this complicated looking thing here. State the number of amino acids that join together to form the section of the protein chain. So what we're going to do here is we're going to count basically what's below here and see what they've connected together. So I think, well, that should be 1 amino acid. I think that's going to be 2. I don't know what's going on there, but to be honest, I'm going to guess though it's going to be 3. That's going to be a 4. This chain here, that's going to be a 5, and that's going to be 6. Because no, it doesn't say different amino acids, just number of amino acids. Yeah, I think this seems weird, but yeah, I do think it's logical. It's just kind of not very well laid out, I suppose. It's just a bit unorthodox, but yep. So you just count up all the weird bits sticking out. So that means it must be 6. Name the weakest van der Waals force between water and gelatin molecules. Well, you can already see here there's OH groups, there's OH groups. Oh, actually it says weakest, not strongest. Well, weakest, I don't know, Van der Waals force is always going to be LDF. I guess you can put probably best to put the full name, London Dispersion Forces. But they will accept LDF. It's always going to be the weakest LDF force, and it's pretty much always going to be around. Even in noble gases, you see London Dispersion Forces. So, but yeah, that was kind of a very easy question. B. Student was investigating the viscosity of different concentrations of gelatin solution. The student was asked to prepare a 2% gelatin solution, which is a solution that contains 2 grams of gelatin per 100 cubic centimeters of solution. The student prepared this solution by adding 100 cubic centimeters of distilled water into a volumetric flask, then adding 2 grams of gelatin. Describe how the student should have made up the solution. Oh, it's a free marker, and it's my least favourite thing to do ever. But basically, this thing here is just something you've got to learn. Okay. Right. Right, here we go. Right, I'm just going to go and start putting stuff in. So, measure, put, this is just one of those things you just got to remember, I'm afraid. Put gelatin into a measuring boat. Right, actually, no. 0A balance with an empty measuring boat. Then add gelatin until 2 grams is on the screen. Then dissolve the gelatin in a small volume of water. pour the water into a volumetric flask. And rinse out the beaker used to dissolve the gelatin. And add the rinsings to the volumetric flask. And then add water until the bottom of the meniscus touches the bottom of the graduation line. Right, I've made several spelling mistakes there due to not actually looking at the text I've been writing. But graduation line, and get rid of the second the and put 100 centimeters cubed. Right, and that should be good. The results obtained from the students' viscosity experiment are shown. Predict the student's result for the viscosity in units of a 10.0% gelatin solution. Okay, well, go through here. When we add another 2%, it goes up by 1. And then we add another 2, we go up by 2. I don't know what's happened there. And then we add another 2, it goes up by 3. So that means if we go up by another 2, we'll be going up by 4. So it would be 11.0, I guess. Bromelain is a mixture of enzymes found in pineapple that aid digestion. Adding raw pineapple to gelatin results in the gelatin molecules being hydrolyzed. The rate of hydrolysis is reduced if the pineapple is cooked. Explain why the rate of hydrolysis is reduced. Okay, well, it's because it's a mixture of enzymes, which means high temperatures cause the enzymes in bromelain to denature and no longer function. There we go. Bromelain can be purchased as tablets that contain 500 milligrams of bromelain. The flesh from a pineapple contains 13.2 milligrams of bromelain per gram. Calculate the mass in grams of this pineapple that would be needed to produce 500 milligrams of bromelain. Okay, so right, so flesh from a pineapple per gram. So let's go and see how many grams we need. 5 of this. There's only one marker, so we can just do it all in our heads. So that's 500 milligrams. Each gram contains 13.2, which means we need 37.8 grams of pineapple. 37.9, I suppose, yeah. Oh, pineapple. On to number 9. Oh, we're getting there. So I am recording this during like one of the hottest days of the year so far, even though it's only spring, but Jesus, it's so hot even at 7 o'clock at night. So I'm boiling right now. But anyway, chlorine is used in the production of many other chemicals. Chlorine can be produced by the reaction of hydrogen chloride with air using the Deacon process, which is this magical thing here. Using the potential energy diagram, determine the activation energy in kilojoules per mole for the forward reaction. Okay, so activation energy, remember, is just how it's basically, oh my mods, this software actually stinks. It's basically going to be this distance here. Right? So now we just need to figure that out, and it's south they start at 0, So that means we can just go across this line. So it'd be roughly for let me 1, 2, 3, 4, 5, 6. 220. No, that seems about right. 220, and remember we got to use these units. There we go. 220 kilojoules per mole. Explain why increasing the temperature in the decon process results in less chlorine being produced. Okay, well, look at this one, right? Remember, it's an exothermic reaction because we lose energy in the reaction, so it must go into the environment. You know, energy can't be created or destroyed. So that means that since it's exothermic, if we increase the temperature, the system will kind of compensate for that by going the endothermic way to kind of reduce the temperature back to normal levels. So that's exactly what we're going to write. There we are. One laboratory method for the preparation of chlorine gas involves adding concentrated hydrochloric acid of potassium permanganate. The chlorine gas produced also contains small amounts of hydrogen chloride gas. To remove the hydrogen chloride gas, the gases are bubbled through water. Finally, insoluble chlorine gas is collected. Okay, so now I need to go and cook up something here. So we need to add, we've already added concentration on acid permanganate. Chlorine gas also contains small amounts of hydrogen chloride gas, bubble water, and then we're going to go and collect it. Okay, so if we're going to bubble it through water, let's just go and do that. So we're just going to have another test tube over here. That's a bit too long. Yeah, that's more like it's probably the same size, but here we are. And then this is going to be a stopper. Please don't block off these tubes, whatever you do. They SQA are not kind about that. They will end your life if these tubes are blocked off. I mean it. So there's our stopper for our tube. And then we'll make the worst conical flask ever. What on earth is this? And then put that there, and we want to bubble it through water, so we'll throw it in here, and we'll just put our tube in there. We'll label this as water, and then we'll collect the gas that's bubbled off, because remember we're getting hydrogen chloride gas. It will get dissolved in the water, and then the gas that comes off it should just be pure insoluble chloride gas, and then we just need to collect it. And what do we do when we want to collect a gas? We're going to use a gas cylinder, gas syringe, sorry. Gas syringe, we have to have a label on it for some reason, and there we are. I'm just going to put gas syringe just to be extra sure. And there we are. And then, we'll just leave it like that. It should be alright. It's only 2 marks. Alrighty, carbon tetrachloride, CCl4, is prepared by the reaction of chlorine gas, Cl2, with methane, C4CH4. Calculate the enthalpy change on kilojoules per mole for this reaction using the following information. So this is basically a big example of Hess's law. We're going to go and move these formulas around so eventually we can get the original equation. So in the original equation, methane is on the left side, but this one's on the right. So we're going to go and flip this over. And what does that mean? well, that means all we're going to do is we flip it round in around, so it'll be CH4 turns into these two, and that means the enthalpy change will now have a different sign. It will be 75 instead of minus. But other than that, we won't need to change anything, multiply anything, because this is just CH4. There's no multipliers. CCl4, that's on the correct side. And these two, they're not in their original equation, but remember, carbon there will get cancelled out because we've moved this onto the other side. And 2Cl, that looks like it's going to be there as well. But maybe we have to fit around this equation first. So we have 4 HCl here, but it's on the right side. So all we need to do here is times this by 4, which means I'm going to quickly run through that with our handy dandy calculator if it wouldn't have been full screen on me for some reason. So minus 92 give us minus 368. But then if we've times this by 4, then this would become 2, and this will also become 2. We'll just see if it all makes sense. So remember, this one's flipped over. So that would, I'll go write it out, flipped over, just to make sure we're all on the same page here. And I won't bother writing state symbols because I'm a rebel who goes against society's norms. We're just going to make sure this all makes sense. So CH4, that's good. That's what we want on that side. And then let's see if we can find 4Cl. Well, that's 2 there, 2 there. So I think that's 4 if we add them together on the left side. Then on the right, we've got CCl4. That's there. And then we've got 4HCl. Now, does everything else cancel out? Well, this is 2 hydrogen over here, so this gets cancelled out by those two, and then CS gets cancelled out by that. So yeah, this all makes sense. So this means is we just need to add up all these numbers here. So we've got 75 minus 98, and then minus 368. That gives us minus 391. So we can just say delta H equals minus 391 kilojoules per mole. And there we are. Ooh, okay. Turn over the next question. Number 10. A student investigated the purity of a sample of magnesium chloride. The sample was dissolved in water and an excess of silver nitrate, silver nitrate, yeah, was added to produce a precipitate of silver chloride. The precipitate was collected, dried, and weighed. The student prepared the magnesium chloride solution by dissolving 2.503 grams of impure magnesium chloride in the water. Explain why the students used distilled or deionized water rather than tap water in preparing the solution. So that means what we would just basically say is tap water contains impurities. And then we're going to list some. Chloride, ions, magnesium ions, or metal ions. Which may react with the magnesium chloride. There we go. So you do have to, looks like this question, you actually have to make some examples, but you can probably just say they contain metal ions and probably get the mark. It's only a mark, okay? Complete the table below to show the most appropriate piece of apparatus that could be used to meet the required volumes. So when we're talking accurately, we're talking about pipettes and burettes, but it's only 20 cubic centimeters. So I think I'm going to go with a pipette. And then 35 cubic centimeters approximately. Well, pull out your old measuring cylinder there. Probably don't use a beaker. That's just a really bad idea. Use a measuring cylinder for somewhat accurate result. But yeah, you don't want to go through the whole process if you're going to put it out a pipette for something that you just need 35-ish cubic centimeters for. The steps required to collect, dry, and weigh the precipitate are listed below. However, the steps are in the wrong order. this is horrific. So we need to complete the flow chart to show the correct order of steps that the student should carry out to collect dried wave precipitate. So we've already started out with E. So then we've weighed the for the paper. So that's good. Oh yeah, okay, I get what it is. It took me a wee while to process what on earth this question was all about. But basically what we want to do then, if we've got the filter paper that we're going to be using, then we're going to actually throw the precipitate through it, and then we're going to wash the precipitate with water to remove any impurities. So this, yeah, because if we fill it for the filter, there might be some extra impurities that have been thrown in through the precipitate. And then, well, it says collected, dried, and weighed, so that means that we probably need to go and put it in the oven first. This dry the precipitate in water. This just get rid of all the water that we've just put in, and then finally we can weigh the precipitate in the filter paper. So the precipitate will be on the filter paper because it's solid. You can't put solid through filter paper, and that means that we'll be able to figure out how much paper is in there. So there we are. 1.393 grams of silver chloride precipitate was produced from the magnesium chloride solution. Calculate the mass of magnesium chloride in grams present in the magnesium chloride solution. Okay, so we've got 1.39 grams there, and we want to figure out the mass of magnesium chloride that was used. So let's go. M equals it's N equals M over FM, or GFM, or whatever you want, and it says 1.393 over 1434.4. Then we're going to just go and run that through our calculator. Divide by 14.4, and then we've got this horrific number here, 0.97. I'll keep it in my calculator just for the safety of it. So then, remember, this is a mole ratio of 1 to 2, so we have to divide this by 2 to figure out how many moles of magnesium chloride there is. So there we go, we've got this. So I'll just write it down. 0.0049, and then now we just need to go and plug it back in. This equation over here. We don't know what mass we're going to get, but we do our formula mass of 95.3. So now I'm just going to times this number by that. I'm going to get our mass of 0.46. Beautiful. The average mass of magnesium chloride in 2.503 grams of the original impure sample was calculated to be 2.403 grams. Calculate the percentage of magnesium chloride present in the original sample. So I think what we're just going to do here is divide them both by each other. And see what we get. And we get 96 pretty much on the dot. Perfect. Ooh, we continue. Always at the last bit of the paper. Oh, can't wait. Differences in physical and chemical properties can be used to distinguish one compound from another. These compounds extracted from orange juice include antioxidants, flavor molecules, essential oils, aroma molecules, and color molecules. Some of these are shown below. Using your knowledge of chemistry, comment on how the difference between chemical and physical properties can be used to distinguish between the compounds extracted from orange juice. Oh boy, this is going to be a bit of a difficult one, but I'm sure we can get through it, just as long as we stick together. So, what we're going to have to do here is this is a this is all the substances we want to distinguish from each other. So we need to figure out like some sort of process that would allow us to find the differences between these molecules. And we don't really want to use stuff like chromatography because that's just a bit lazy, I guess that's what they would say. But stuff that's pretty easily done and will be concrete in terms of tests. So,
Hey folks, Mash is back. I just got nice some water. I've had a think about this, and I might be on the verge of something resembling a solution. So if you like a look at these, the main difference, the main deciding factor, you know when you're playing Guess Who and you're trying to like kind of cut the board in half. What I've figured out here is what we want to do. Let's have a look at all these. You see some of them are saturated and some of them are unsaturated. So first step. Um, test for unsaturation by adding substance to bromine water. If it decolorizes the bromine from red to colorless, yeah, just be real clear here what I mean by decolorize. Then the molecule is unsaturated. It is, yeah, unsaturated. But if it does not, the molecule is saturated. So, well, what does this mean in our, how does this help us? Well, because this molecule here, that's unsaturated, I put a line through unsaturated. Once this one's saturated, unsaturated, saturated, saturated, unsaturated. So there we go. So now we've split away 3 and we can test them individually. So now we'll have a look at these and see if we can distinguish any differences. So let's keep writing. Move the substances that were saturated, unsaturated, I mean, into a different group, and then test their water solubility. So if you have a look at this one, these are all fairly. Vitamin C here is a very polar molecule, but this beta-carotene, this is completely symmetrical, well, pretty much. I mean, it's going to be pretty non-polar, and so is limonene. Like, yeah, there's some stuff there, but it's not much. The molecule that tests higher that has the highest water solubility, i.e., being able to added to water the most without saturating the water is it's going to be vitamin C. The remaining 2 molecules are both non-polar, so won't be dissolved by water very well as they are insoluble. Yeah, I'll just go and clean this up. We'll just say, you just pretend those 2 are pretty much insoluble. The molecule that is dissolved by water is vitamin C. Non-polar, so soluble. And then all we need to do now is distinguish between beta-carotene and limonene. And a way I think we can do that is beta-carotene. I don't think we can oxidize anywhere, but limonene we can. So then try and oxidize the remaining 2 molecules. The one that successfully reacts with oxygen at low temperatures is limonene, as it is a terpene which can oxidize to a terpenoid. The oxidized product would give off an unpleasant smell. And the beta carotene would take a lot more effort to a lot more heat to oxidize, and would burn. I hear my dog in the background barking away. Oh, it's not exactly the ideal study environment, but only one I have. Need to oxidize. Yeah, so it's a bit. I mean, it's a bit iffy between beta carotene and limonene, but whatever, mate. You can't stop me. So next up, what we have to do is have to separate octanol, ethylene butyrate, citric acid, and fructose from each other. So, first thing we're going to do is that citric acid is an acid. Then move to the saturated compounds. And test pH. The one that has a pH lower than 7 is going to be citric acid, as it has lots of carboxyl groups. Release hydrogen ions. There we go. So now we've got citric acid out of the way. We just need to distinguish between octanol, ethyl butyrate, and fructose. So, okay, so what we can do is yeah, let's go and attempt to react with a carboxylic acid. Would be this is the fructose is the only one with OH molecules because we've removed citric acid from the equation, so that means it would have to be fructose, as it is the only chemical remaining that has hydroxyl groups that can react with the carboxylic acid in a condensation reaction. Right, so now what we've done now is we've eliminated those two. We just need to distinguish between octanol and ethyl butanate. And I think the best way to do this is probably to perform hydrolysis on ethyl butanate, hydrolysis, and then it won't do anything to octanol. I mean, what you could also do is you can also say oxidize both of them, and then one of them will turn into an acid. That might actually be a bit better, actually. That's probably a bit simpler. Main two compounds, they should both be oxidized. The one that has a pH below 7 after being oxidized is going to be octanol, as oxidizing it will form a carboxylic acid. While ethyl butanate is unaffected. Oh boy, that was a lot of work. And a lot of water had to be drunk to cook up that solution. But it's all done and dusted now, so I can finally move on to the last question. Yes, I can have my tea. The label from a bottle of Pine Fresh Bleach Cleaner. Yeah, everyone loves Pine Fresh Bleach Cleaner. Oh, it's lovely, jubbly stuff. Is as shown, and it's formulated to kill germs and roost aids. It's got these ingredients, and please, guys, don't keep out of reach of children. Surfactant molecules are added to bleach clean to act as detergents, soaps, or emulsifiers. Information on the three of the surfactants of bleach clean is shown in the table. So complete the table for compound B. So we've got type of surfactant and then head group. So is it going to be ionic or is it going to be non-ionic? Okay, well, looking through here, I believe it will be ionic because it's got this chlorine atom, a chlorine ion, I should say. Sorry. So let's go and say ionic. If I could actually write small. And then for the head group, we need to have a look at here and see if there's anything going on. And it looks like it's going to be positively charged. Because it's attracting that chloride ion, or chloride, whatever. Right, cool. Compound C is a soap molecule. Soaps can be made with fat and oils. Name reaction used to make soaps from fat and oils. So this one is, when we do this, it's going to be called alkaline hydrolysis. It's just one of the things you just gotta remember. But you know, it's like it is hydrolysis. You are splitting up fat and oils, but then you're changing it in using an alkaline as a catalyst so you can make it a salt essentially. Oh yeah, sorry. During the description now, the alkaline would then neutralize the carboxylic acid you get when you hydrolyze a fat or oil, the fatty acid, which would leave you with a salt, which would be a soap. Fun fact here, maybe you can share that on the dinner table. So, soap molecules allow oil to mix with water. Explain fully the cleaning action of compound C, which is this thing down here. You wish to use diagrams to help with your illustrate your answers, but we're too cool for that. So I think I'll just go and write that as is. Yeah, there's a lot of stuff you can get marks for here. Well, not, yeah, sort of. So, compound C has a hydrophilic, extend this out massively. Philic polar head and a hydrophobic non-polar tail. The hydrophilic head dissolves in water, and the hydrophobic tail dissolves in oil. This causes the soap to form mycelials around droplets of oil, preventing them from sticking, allowing them to be removed easily. And I believe that's all 3 marks done dusted. And I'm getting tired, so I'm not going to do any more. The structure of an emulsifier molecule is shown below. We've got this thing here. State how emulsifiers are made from edible oils. So, okay, well, I mean, looking at the diagram would probably give you some clues. So what we're going to see here is that you've got this glycerol molecule here. And then we react it with edible oils, because it says it's made from edible oils. So we're just going to say by reacting edible oils with glycerol. And there's about a billion different ways you can write glycerol, but there's only one cool way, which is just to do nothing, because we don't like wasting time around here. By writing, and I believe that will give you the mark, if I'm reading that correctly. Sodium hydrochloride, everyone's favorite chemical, is the main active component in bleach, compound in bleach. Sodium hydrochloride is produced by reacting chlorine with sodium hydroxide solution. A chlorine molecule has a pure covalent bond. Explain what is meant by pure covalent bond. It will be a both nuclei, both atoms have the same electronegativity. That's not how you spell electronegativity. That's nothing to do with electronegativity. Cheers. Negativity. And thus share bonding electrons evenly in a nonpolar bond. Boom. When the chlorine is reacted with sodium hydroxide solution, an excess of sodium hydroxide is used. Suggest why an excess of sodium hydroxide is used. Okay, so that basically means that we want to get rid of all the sodium, all the chlorine. So we're just going to say to make sure that all the chlorine is used up. Is reacted, probably. Is reacted. But there's actually quite a few different reasons. I'll pull up the marking scheme right now. I'm not pulling out all these answers just from my head. But as you can see here, there's actually quite a few. You can say it's cheaper, less expensive reactants for this reaction. You can say that excess would be neutralizing the acid anticleator, yada yada. So yeah, remember you can think outside the box for these. You don't need to just say what I'm writing down. I'm just doing the simplest things that take me the least amount of time to type, to be honest. So, next question. The bleach cleaner and equilibrium exists. The label warns that the bleach cleaner should not be used in other products as it may release chlorine gas. Explain clearly why mixing the bleach with an acid would shift the equilibrium to right using the release of chlorine gas from the bleach cleaner. Crazy. So if you mix it with an acid, that would mean that you actually have more of these hydrogen ions lying around because that's what an acid is. It has lots of hydrogen ions. So that means that it would shift the equation to the right, focusing on producing chlorine gas, which is toxic and not something you should be near. So let's write it down. So adding acid adds hydrogen ions, which increases, which favors the forward reaction. Increasing its rate. So chlorine gas is produced. The concentration of hypochlorite, OCl, in bleach can be determined by a redox reaction that involves two steps. Step 1, excised acidified potassium iodate is added to the bleach. This converts the iodide ions into iodine. Step 2, the iodine produced in step 1 is titrated with sodium thiosulfate. Write the oil-electron equation for the reaction taking place in step 1. So this is the reduction reaction, so we have to go and find what is being reduced. And it seems to be quite easy to see that, well, reduced is when you add electrons onto something. So let's have a look at break this down. Okay, well, this chlorine atom is bonded to an oxygen, and then it goes here, but it still has a negative charge. So that means probably that's going to be reduced because you're adding electrons on. I mean, it's in comparison to the iodine, which is very clearly being oxidized as it loses electrons. So yeah, let's just go and write that down. So we know that it's OCl, and then we have to put living state symbols. Okay, state symbols are not required, but also I'm going to write them in anyway because I'm very cool and write state symbols for everything. Just kidding, I don't, but here we are. So then it goes to Cl minus. So when you're doing this, there we go. So obviously there's a few more elements involved in this. So we're going to have to go and make sure this is balanced. So first step is, are the two main elements balanced? Yes. But then we have this oxygen atom that just up and disappears. That's horrific. So to balance out the oxygens, we need to have a hydrogen, a water molecule, and that's going to be in the liquid state. So that pretend that's an L. And just realize that is actually horrific A. So there we go. So now we have hydrogen, but now we need to get hydrogens in here. So we're going to have 2H plus. So that means that's balanced. But now this is 2H plus, and we have to have the same charge on both sides because now we're just messing around. Which means we have to have electrons to kind of balance out the hydrogens. So it'll be 2E minus plus that. And there we go. All together. And state symbols for the hydrogen ions. It's Aquarius, guys. There you go. That's what you get. Oh, and this is the last question. Oh, I'm finally free. A 25 cubic meter sample of diluted bleach was transferred into a conical flask and excess acidified potassium iodide was added. The iodine produced was titrated with 0.098 moles per liter, whatever that is, sodium thiosulfate, requiring an average volume of 9 cubic centimeters to reach the endpoint. Calculate the concentration in moles per liter of sodium hydrochloride in the diluted bleach. Righty, we're going to have to do some maths here. I know, crazy. So, how are we going to go and start this? Titrated with the volume of the endpoint. So how many moles of classifier. So if it is that, let's go and figure that out. So remember, N equals CV, concentration, N is moles, C is concentration, V is volume. So concentration is 0.098 moles per liter, and then volume, it's not 9, it's 0.009, because remember we're all doing it in liters. So we'll pull out our calculator, and this will give us an astonishingly low number. Yep. Oh, I love writing loads of zeros. Oh, there's an, that's a really bad 8 as well. There we go. 0.00082 moles. Don't mean to put state units in the middle of the thing, but here we are. So that means we now know that we've got 0.00082 moles of this, and we want to calculate the sodium hydrochloride, which is we can figure out by so hydrochloric is this thing here. So we can figure out that this will be this concentration of this this stuff here would be equal. Will be if we divide the amount of moles we got for this, we'll get the number of iodine things that are produced, which would then be equal to the number of moles of this. Whew, okay, so it's a 1 to 2 molar ratio. So we'll divide by 2, giving a number. Oh, it's getting lower and lower. And then this would equal the amount of hydrochloric ions. So then it's 25 cubic centimeters. So we just need to go and do the N equals CV thing again. So now we know that it's this many moles. Concentration we don't know, but we know that the volume is 0.025. So then we divide this by 0.025. We get 1.17.4, and I'll just double check that it's not going insane. Yeah, it is right. We're so solid. Concentration is 0.018. We'll say. Then we'll go 7.6. Come on, we're not that bad. Moles per liter. And there we are. End of question paper. So yeah, thanks for watching, folks. I'll get this up before the chemistry exam, hopefully. And I know it's been 2 hours and whatever minutes, but thanks very much for watching. It's been a real pleasure teaching you all and learning together, as they say. But thanks for watching, folks. MASH is out!